Okay, you guys. This is probably one of my favorite statistics lessons. I love it so much, and you'll see why at the end. It's awesome. Very entertaining. Um, so grab your notebook. You'll need to take a couple notes, pen or pencil. You may need a calculator. I can't remember. But definitely grab your Eureka book, and then you need either your computer or a phone. Okay. Quick reminders before we jump into this awesome lesson. We're gonna have a statistics unit quiz tomorrow. Now it's not this giant thing. Um, Basically, what I did was I gathered some data from all the middle school teachers. I came up with some random questions to ask them that we could use for statistical analysis. Um, and basically wrote some questions just like you've seen the last couple weeks. Um, so like drawing a dot plot or making a scatter plot, what do the residuals mean, that kind of stuff. Using that data. So it's gonna be entertaining data from your teachers, which will be cool. So that's kind of the gist of the quiz. Again, it's more just to see like how much you've learned the last couple weeks, and then we'll have the actual like end of module project, which will be kind of just a refresher once we get back from the holiday break. Okay. Today oh, so many fantastic memes and cartoons with this lesson. Today we're going to be doing lesson, whoa, I throw my headphones everywhere, lesson 19 in module 2. The goal for today is to be able to interpret the value of a correlation coefficient and explain why correlation does not imply causation. And if those just look like a bunch of foreign words right now, that's fine because you will understand it by the end, I promise. Okay. Here we go. Quick review before we jump into new stuff. With data, if we're given some data, we can use a line of best fit. So we have some data, kind of looks like this. We can use a line of best fit to basically predict other data. Okay, so if we're looking at, for example, my love for dessert on a scale of 1 to 10, and how many pies I eat yearly. I don't know. I'm totally just making this up on the spot. Now I still lost my the pen that I usually write with, which is why the handwriting is not fantastic today. So basically what it's saying is that we can calculate this line of best fit and use it to predict data, meaning if my love for dessert is here, so I'm looking at a 7, let's say a 7 on a scale of 1 to 10. I can predict someone's love for, so I can predict how many pies they eat yearly based on how much they love dessert, is basically what that line is helping us do, right? We can say, well, if somebody loves dessert on a scale of 1 to 10, at a 7, they probably eat, I'm totally just making this up, 10 pies a year. Okay. So that's what it means by we can use it to predict data. Okay. Now, residuals are going to be the prediction error, meaning the difference between the actual data point, so say this data point, and the data point on the line that we would predict for that variable. Okay, so for example, if I said, well, somebody loves dessert on a scale of 1 to 10 out of 4, our predicted number of pies they eat is somewhere around 4, but the actual data point for this person, again, this is all made up, was 8. right? So the prediction error, the residual, is this distance right here, okay? So again, this is just a reminder of stuff we've learned. And then residual plots. Residual plots. Basically, we're looking at your x value and your error. So that residual. It's basically going to look like this line with the data just, tilted, okay? So we would have dots, a couple dots above, a little below, kind of like that, okay? Now, if we're looking at residual plots and we're asked if a linear line is a good fit for the data, if there is a clear pattern in the data, so if you can see that like it goes like this, or like this, or like an arc of some kind, if there's a clear pattern in your data on the residual plot, it means that whatever model you chose, so linear versus like exponential. So say we chose a linear line here and there was a clear arc, it would mean that your data is actually exponential, not linear. Okay? Or vice versa. If we modeled with a exponential prediction line or exponential line of best fit, and there's a clear arc or pattern in the data for the residual plot, it means that our data was not exponential. Okay? Again, this is all just a review of yesterday's video. So here we go. Let's jump into lesson 19. We got a lot to do today. Lesson 19, example 1. I did not mean to do that. Okay, here we go. Linear relationships can be described as positive or negative, and I've kind of hinted at this before. So which one of these is positive versus negative? And the hint here is think slope. Okay, so maybe think about that for a second. Which one's positive, which one's negative? Now, I said think of slope. What I mean by that is, let's say that the line of a best fit that we predict for this data is that, and let's say that the line of best fit we predict for this one is something like that. Okay, think slope, right? Would the slope for the graph on the right be positive or negative? Well, as x increases, y is also increasing. So we would call this a positive relationship, okay? Whereas the one on the right, as x increases, y is decreasing. So we would call that a negative relationship, okay? So that's just basically tying back into slope, okay? Positive and negative slopes. Now there's a point to this. Let's look at exercises 1 through 4, lesson 19. Number 1, we have a positive linear relationship. Okay, scatter plot number 1, we have a positive linear relationship, meaning as x is increasing, your y is also increasing. Does the value of the y variable tend to increase or decrease as the value of the x increases? I literally just said this, so hopefully this is making sense. Okay, as your whatever your x variable is, as it increases, so as we're going from 20 to 30 to 40, right, the y value also tends to increase. So we're low here, we're getting higher on the x here, and we're also getting higher on the y, right? Up here we're getting a little bit higher on the x and a lot higher on the y, etc. It keeps going up and up and up. Okay, so we would call that, again, a positive slope. And then the opposite would be true over here, right? As x increases, our y is decreasing. Okay. Hopefully you're seeing that and that's making some sense. Let's see. We just talked about that. Let's see. Really, this is just a good place to stop and write down the notes for this. So I would definitely write this down. If we have a positive linear relationship, the x values will increase and the y values will increase. But if it's a negative linear relationship, the x values will increase and the y values will decrease. Right? So increase and increase, decrease, or increase and decrease. Okay, so negative, positive. Basically, you can think of the negative one as opposites. As x increases, y decreases. The positive relationship would be equal. Your x is increasing, your y is increasing. Okay. Okay. There also is such thing as no correlation, and this is essentially the same thing we talked about a couple weeks ago or a week ago when we said that there's no relationship, right? If you have a scatter plot and your dots are just totally all over the place, random, there's no clear pattern, it means there's no relationship. Now, another word for that is correlation. Okay? So let me write that out because that is very important. Correlation, that is very big. Correlation is basically just relationship. So is it a positive relationship, negative relationship? Is it strong? Is it weak, etc.? Okay, so that would definitely be a great thing to write down. Here's a good example, and this might be a good thing to just kind of sketch out really quick. A positive correlation would look something like that. A negative would look something like that. No correlation would be totally random. Okay. And again, this is kind of a review of stuff we've already talked about. We're just calling it correlation now instead of relationship, right? Or correlation instead of slope, right? Okay. Exercises 5 and 6. And again, I am kind of zooming through this. You don't need to write all this down in the Eureka book, like answering all the questions. I would mostly just focus on writing down kind of what I highlight and say this is good to write down. Okay. So exercises 5 and 6. So we have 2 more scatter plots, scatter plot 3 and 4. Think about, and you could write these ones down. Think about this. Is scatter plot number 3 positive or negative? And then number 4, is it positive or negative? And think about what else do you notice. So it could be like direction, linear versus exponential, strength of relationship. So maybe think about that for a minute. Pause, think about it, and then come back. Okay. Can't remember if I actually talk about this in the next slide. Yeah, I kind of do. Okay. Let's take a look at this. What is happening on this scatter plot 3 as x increases? Okay, so what's kind of the pattern here? So we're starting off kind of low, but then we kind of jump all over the place. But you notice that there's kind of a trend in the upward direction. It's not like super steep, but there is a slight trend going up. So we would call this a positive correlation. Okay, positive correlation. What about 4? Well, 4 is basically the same thing, right? There's an upward trend, so it would also be called a positive correlation. But what's the difference between the two? Okay, and yes, one line is lower than the other, right? But that's not really what I'm talking about here. What I'm referring to is the spread of the data. Notice how the data over here is fairly close to that line I drew, whereas this data, the residuals, the prediction error is a lot bigger. Okay, so that is referring to the strength of a linear relationship. Okay, so why would scatterplot 3 be weaker than scatterplot 4? Well, because scatterplot 4 is much more consistent. Think back to when we talked about like battery life of the different brands of batteries. The more consistent your data is, the smaller the residuals, the smaller the deviation, which means we can use it as a much more accurate piece of information. Whereas if stuff is more spread out and random, it's not going to be very helpful, right? It'd be like something saying, well, if there's a claim that like, if you eat chocolate before a test, your test scores are gonna be better, right? If the data was kind of all over the place like this, though, we wouldn't really want to trust that data. However, if the data was closer and a lot more consistent, it'd be a lot more trustworthy data. Okay. So that's why strength of the relationship is really important, because you could have a trend in the data. It could be like an increasing trend, but if it's an extremely weak relationship, it doesn't mean anything, right? You want more consistent data. Okay, let's take a look at exercise 8. What would a scatter plot with the strongest possible linear relationship look like if it's positive? So stop and think about this for a minute and maybe just sketch one out really quick. It doesn't have to be detailed with a lot of dots or anything, just a few dots is fine. Think about what that would look like and then come back. So what do you guys think it would look like? The scatter plot with the strongest linear relationship. And again, strength of the relationship is referring to how spread out your data is, right? How far it's deviating from each other, right? So think about those distributions we looked at, right? The closer your data is, the less the deviation, right? The more accurate it is. The less spread out it is, the more accurate and the stronger it is. Okay? So that's what I'm referring to when I'm talking about the strength of the data. It's more consistent, it's less spread out. So what would a scatter plot look like with the strongest possible positive linear relationship? Can't remember if I have an example of it. Nope. So actually, yes, I did. Okay, we'll get to it. So think about that for a minute and I'll answer it in just a moment. But think about this again. What would a scatter plot look like that has the strongest possible linear relationship, but it's negative this time? So maybe sketch that out too. Okay. Hopefully you did that, because it's a really good thinking exercise here. And let's talk about these graphs now. So looking at these scatter plots, what do you notice? Maybe stop and think about it for a minute. What do you notice? Well, most students in class would mention something about, well, this looks like a positive relationship, right? As x is increasing, y is increasing. This looks like a negative relationship, positive, positive, okay? They would also maybe compare the spread of the data, right? So, for example, this one in the top left is very consistent, meaning that it's an extremely strong relationship, okay? And it also looks steeper, or I should say a more positive slope compared to like this one, for example. See how this one is that, the other one is more like this, right? That's what I mean by a more positive slope. Let's look at the top right. Top right. It is a negative relationship, right? As x is increasing, y is decreasing, but it is much more spread out. So it's more scattered, which means it's not as accurate, right? It's less consistent. So we would call that like a weak or maybe moderately weak relationship. Okay. Let's look at the bottom left graph. It is positive, right? As x is increasing, y is increasing. It's definitely more consistent than, say, this graph, but it's less consistent than this graph, right? So we would call this maybe a moderate or moderately strong. I'd probably say moderate, but could be moderately strong relationship, meaning it is fairly consistent. Right? It's more spread out than this one, but way less spread out than that one. Okay, and then let's look at the bottom right. This one's more of a red alert, right? It is a positive, meaning as x increases, y tends to increase, but it is very, very scattered, meaning it is very weak. It's a very weak relationship, meaning it wouldn't really help us that much. We wouldn't learn very much from this data set. So it's not very accurate. It's weak. Okay. It's very scattered. Okay. So there's some adjectives we can use to describe these relationships. The question though is, how could we mathematically measure the strength? So how weak or strong a linear relationship is between two variables. How do you think we could measure that mathematically? Well, this is a lot of notes, and I would definitely write all this down. Okay, please, please, please write it down. Measuring the strength and the direction of a linear relationship between two numerical values. This is what we refer to as the correlation. I'm going to maybe highlight this in a different color too. The correlation coefficient. Okay, there's your big vocab word here, correlation coefficient. Okay, correlation coefficient is a way to measure the strength and direction of a linear relationship between two numerical values. The symbol that we use for the correlation coefficient is R. Okay, so if you ever see R equals, it's talking about the correlation or the strength and direction of a linear relationship. Okay, the value of R will always be between 1 and -1, including -1 and 1. I don't know why there's a negative there. There shouldn't be a negative. Between -1 and 1. Okay. Now, +1 would mean the strongest positive correlation possible. Okay. Meaning the dots are going to be exactly on the line. Okay, that's what it means by strongest, and positive meaning it's going up. -1, an R of -1 would mean the strongest negative correlation, meaning, again, we still have that, the dots exactly on the line, but this time the line is going down. Okay, so it's going to look something like this. Okay. An R of 0 would mean that there's absolutely no correlation, meaning we have this graph, we have a ton of completely random data. There is no pattern, there is no relationship. That would give us an R of 0. Okay. The closer to 0 your correlation coefficient is from either direction, the weaker the relationship. and the opposite is true. The closer to negative 1 or positive 1, the stronger the relationship. Okay, there's a lot to take in. Pause the video, write that highlighted stuff down, maybe even draw a couple examples like I did over here. Okay, that might help, and then come back. Okay, let's talk about correlation coefficient. Again, correlation coefficient is measuring the strength and direction, think slope, of a linear relationship. Okay, and this is, I'm going to emphasize this is for linear relationships. Okay, so let's look at these graphs and talk about them. Okay, what do we think about them? Look at these, maybe pause the video, think about the words like strong, weak, moderate, no relationship, positive relationship, negative relationship. Maybe try to identify which one of these would be what. So which ones are positive, which ones are negative, which one has no relationship, which ones are strong versus weak versus maybe moderate. Okay, so pause the video, see if you can think about which of these graphs are which. Okay. All right, here we go. This would be a fantastic thing to write down, and it does not have to be like word for word. You don't have to draw the graphs perfectly. Okay. But all this information is very important. Again, the correlation coefficient, which is noted by R, we're talking about strength and direction. Okay. So what we notice, we have positive relationships, which means that the slope of the graph is going up. Okay. We have negative relationships, which means that the slope of the line is going down. And then we also have strength. So that was talking about direction. Now let's talk about strength. Strength meaning, is it really accurate data? Is it consistent? Would it be very useful in predicting things? Okay, that's what I mean by strength. Here, let's just use a darker blue. A perfect correlation, so you could have positive or negative perfect, would mean it's in a perfectly straight line. Okay, perfectly straight line. Okay, a high positive or a strong, it says high, but it's really another word for it would be strong. Okay, a strong relationship, we'll use gray for strong, would mean that the data is pretty consistent, but it's not perfect. Okay, pretty consistent, but not perfect. We also have what we would call a weak relationship. Let's use yellow. Here they call it low, but it's talking about weak. Okay, a low correlation, positive or negative, would mean there is definitely a pattern, but it's even more spread out than like a moderate relationship or a very strong relationship. Okay, it's a lot more spread out. And then we have this magical graph in the middle that has absolutely no correlation whatsoever. It is completely random. It's all over the place. It doesn't increase or decrease consistently at all. It's just completely random. There's no correlation. There's no relationship. Okay. So this would be a great thing to write down. And kind of the rule of thumb as to when we have a weak versus moderate versus strong relationship is written below here. Let's see, I used blue for strong. A strong relationship would be a correlation coefficient, so R equals a 0.7 to 1. 0.7 to 1, and that can be positive or negative. Okay, so it could be like negative 0.8, right? Negative 0.8. Another rule of thumb for moderate, well, let's use maybe purple. Moderate, a moderate relationship, meaning it's not weak, but it's not a strong relationship. So we could use it to predict stuff, but don't expect it to be like very super accurate. Okay. So a moderate relationship would be a correlation coefficient of 0.3 to 0.7, and this could be positive or negative. Okay, and I'm going to get into how to calculate R in just a minute, so don't stress about that yet. And then a low relationship or a weak relationship would be a correlation coefficient from 0 to 0.3, positive or negative. Okay, and really one would be like your totally perfect. Positive or negative one would be totally perfect. And 0 would mean absolutely no relationship whatsoever. Okay, so again, this is a very good rule of thumb. And we'll get into kind of how this helps us in just a minute. So this is how we calculate correlation coefficient, R. Okay, this is correlation coefficient. This will tell us the strength and the direction of any linear relationship. Now, I am not going to make you calculate this by hand. This is how you would do it, and it is fairly straightforward. It just takes a bit of time to do it. So I'm not going to make you do it by hand. We're going to use the computer again. But you'll notice maybe some familiar things in here. Right, this is looking at deviation from the mean. Okay, deviation from the mean. This is deviation from the y mean instead of the x mean. Right, we're squaring it. We're finding the sum of those. We're taking the square root. So this right here is actually the standard deviation, right? Or almost the standard deviation. We actually divide the standard deviation by n-1, but it's almost there. So you see some very familiar things here. So that I wanted to show you that just to kind of tell you what's going into the correlation coefficient, right? It's looking at deviations, right? How scattered the data is, and the slope of the data. So if it's positive or negative. Okay. So this is basically telling you strength, and this is telling you direction. Okay. Okay. So what we're going to do is we're going to graph example 4. Example 4, lesson 19, example 4. I'm going to grab my book in the other room so I can do this with you. You're going to graph it basically the same way we've been doing it this whole time. You're going to enter the data on Desmos, do the y1 tilde mx1 plus b. Okay, and then I'll show you where to look. So here we go. Here we go. We are going to do a new graph. Okay. You're going to click on that little plus button in the top left corner to get a table in there. Again, this is going to be lesson 19. Lesson 19, example 4. So here we're looking at shoe length and height again. But this is from 10 men this time. Okay, so go ahead and enter that data. I'm going to enter mine. Again, I'm doing this in front of you just so you can see exactly how I'm doing this. So if it gets annoying, just know that that's why. That's 10. Last one. Okay. Ah, here we go. Okay. So if you don't have your data entered yet, just pause the video and then come back when you're ready. All right, now we're going to do the same thing we did before. We're going to change the view so we can actually see our data. So your x, again, you don't have to do these exact numbers. I'm going to do, actually, we'll do -5. And our biggest x value, it looks like, is almost 13. So I'm going to do 15. Okay, and then my y-axis, again, I always like to see the axes, so I'm going to do -10 maybe. And my biggest y value, it looks like, is 74, I think. So I'm going to do 80. Okay, so now we can see our dots. This is great. You can already see on this scatter plot, without even having the line, that the data looks linear, right? It looks positive. And if we were to just guess here, right, would you say it's a weak, moderate, or strong relationship? Okay, think about that before we do anything else. Then when you're ready, type in on a new line the y1. Okay, let's see if I can remember how to do tilde. I should really just like write this down. There it is. Y1. Ooh, and make sure your y is not capital. Okay, not capital Y. Regular old Y. Y1 tilde mx1 plus b. Okay, you should get that box that pops up. Okay, I'm not gonna ruin it this time. There we go. Okay, you could plot the residuals. So you could take a look at the residuals plot. Okay, looking at those residuals, we see that the residuals look random, so the linear line is a good fit. So it is linear data, but let's see how strong it is. And to see how strong it is, we're going to look at that correlation coefficient. And that information is right here. Now you'll notice there's an R and there's an R squared. What we are looking at is just R, right? The correlation coefficient is R. Correlation coefficient. Okay, so the R here, to write this a little bigger, is 3.6. We'll round it to nearest hundredth. Wow, looking at the slope there. Hello. I was like, that is not right. R only goes up to 1. Luis. Okay, the R was 0.65. Okay, so what does that tell you? What does that tell you about this relationship? Well, think about it before looking back at your notes. The R is positive, so that means as x is increasing, y is also increasing. So we have that positive slope, so that's good. And then the strength of the relationship. So again, okay, we have positive. So let me just write up a little positive. So our correlation, our relationship between shoe size and height is a positive linear relationship. So we're good there. We know it's linear because the residual plot is random. We know it's positive because the R is a positive. But what about strength? Well, we have an R of 0.65, okay? Which means that it's definitely not weak, okay? I would say that it's moderately strong. Meaning if we wanted to, kind of going back to the first example when we talked about shoe length and height, if we were like predicting somebody's height based on their shoe size in a crime scene investigation, it means that our prediction based on this line of best fit and this correlation would be pretty accurate because it is a pretty strong relationship. So how cool is that? Based on just this information alone and using some basic statistics that you learn in ninth grade, right? We can predict really cool stuff like that, right? That's how basic prediction with really any relationship works, right? I know I've talked about this before, but my actual degree was in cognitive science, so how the brain works. So basically talking about like behavior and psychology, right? How what patterns there are in human behavior. Okay, and this is the type of information that helps us kind of know the trends in human behavior and can predict behavior. So think of crime shows, right? Um, like there's that crime show, Criminal Minds, right, where they have a behavioral analysis unit, the BAU, in the FBI, and basically they take data like basic basic statistical data like this and use it to help catch like serial killers. Like it's crazy. It's crazy. I love statistics. I'm getting super nerdy on this, but it's awesome. Like basic statistics that you guys are learning right now can help you predict stuff like that. And it can help you, like, if you see random Facebook articles or whatever on like, does chocolate actually help you be smarter, right? Stuff like that. If you can find the actual data set, you can throw it in Desmos real quick and actually see how accurate that article is. Okay, it's super cool. And most articles that are actually based on scientific information will give you, they will actually give you the correlation coefficient, the number of data points, the slope, meaning the increase or decrease, like how, if it's positive, negative relationship, etc. They'll give you that information. So, for example, my dissertation that I did was all about. I'm totally going off on a tangent here, but my dissertation was about perception and how accurate our perception is. This is a very vague explanation of it, but the paper that I had to write and published with it had a ton of this basic statistics in it, right? I talked about correlation coefficients, right? I had like the data sentence, so like what the test actually was. And then you have to put the statistics. So any actual science-based peer-reviewed article, okay, that is real information, no false news stuff, will have the correlation coefficient. And now you guys know how to interpret it. How freaking cool is that? Okay, I'm getting so nerdy about this, but it's amazing, right? Basic stuff that you guys are learning in ninth grade can help you filter through all the crazy information there is in the world. Okay. Okay. Whew. Soapbox over. All right. So that correlation coefficient was 0.65, I believe. So yeah, we were good with our guess there, with it being moderately strong. Okay. Like I just like went off on this huge tangent and went like cold turkey back to stats here. Okay, so we need to take a break, cool down from my rant. That's fine. I feel like I need to. It's cool. We're good. All right, time for you guys to practice. You're going to be practicing using lesson 19, exercises 18 through 24. Okay, so it gives you some data, then asks you some questions about it. So like, do you think it's a strong relationship, a weak relationship? Is it positive versus negative? Interpret the R. And again, whenever you are asked to interpret the R, and this might be a great thing to write down. Oh, I guess I don't need to write it down. It's basically right here for you. I'm way ahead of myself. Whenever you're asked to interpret the R, make sure you include strength and direction. Okay, so here's kind of a really good guide to that. right? If you're given data and you find a correlation coefficient of, let's say, somewhere between 0 and 0.3, or maybe it's 0 and negative 0.3, right? You could say it's a weak positive relationship based on that information. So this is a really, really good guide to have. So maybe like take a picture of it or write it down. It's a lot of stuff to write down, but this is like a fantastic guide to have for this class, or just in general if you like to look at science information. Okay, so go ahead and practice that. Let's see. And I do want to kind of touch base on these really quick, kind of just tying stuff together. How is the slope of the line of the best fit and the value of the correlation coefficient related? So think about that. We have the line of best fit, the slope for it, and the correlation coefficient. Well, again, correlation coefficient touches on the strength of the relationship and direction. Slope though talks about direction, right? It doesn't really give us any strength information, but it does give us direction, so positive or negative, right? And the other question here is, why is it important to know if a relationship is strong or weak? And I kind of went off on the tangent on this. But if we look at information and then we're given an R, like they sneakily just like thrown an R in there, and it's like an R of 0.1, right? You're going to know it's an extremely weak relationship, and we should not rely on that data. Okay, it means it is not an accurate depiction of the data. Okay, so that's kind of why that's important. There's one more thing I want to kind of review real quick, and then I'm going to go over one more huge concept. So please stay with me through this because it's huge, and then I'll show you some hilarious pictures, and then we're done. Okay, so think about this. Correlation coefficient between sodium content and the number of calories for fast food had an R, or a correlation coefficient, of 0.79. Okay, this indicates a strong, right, because it's above 0.7, positive or negative, and it's positive relationship, meaning that items, right, if we picture a graph here, we have a strong positive relationship, so it's a positive slope and it's pretty strong, so the dots are going to be pretty close there. Okay, so this means that the items with a higher sodium content, so the higher on the x, the more we increase on the x, the sodium, or the items with higher sodium content tend to have higher number of calories as well. So as the sodium increases, the calories tend to increase as well. So my huge question for you, and this is very, very, very important to think about, is the number of calories caused, this is a very important word, caused by sodium content? Think about it. The number of calories caused by sodium content. And again, the keyword there is caused. It's a huge word here. Well, the answer is no. No. Okay, there's this thing called the third variable problem, and it's not something you're going to be tested on, but it is a very important thing to think about right now. A third variable problem. This means that, yes, in this particular case, we were looking at sodium content and number of calories. And our graph and our correlation coefficient show us that typically the higher the sodium content, the higher number of calories. But that does not mean that the number of calories was caused by the sodium content, right? There could be a huge number of other factors that are coming into play, right? It's not just sodium. Maybe it's fat content, maybe it's carb content, etc., right? There's other things that go into it. So it's not that that sodium causes calories. It may be a factor in it, but it doesn't cause it. This gets me to my next huge giant point, and this is one of the biggest things in statistics at any level. Correlation does not equal causation. Please, please, please write that down. Highlight it, write it on your forehead and permanent marker. Okay. Correlation, meaning the strength and direction of a relationship, does not equal causation. So just because there's a correlation between two things or a relationship between two things does not mean that they are actually causing each other. Again, this is one of the biggest concepts in statistics and one of the most important things you can take away from this year, in my opinion. Okay. And we're going to look at some hilarious pictures depicting this. Okay. So let's check these out now. And this just brings my point home that correlation does not mean causation. Okay, let's take a look at this graph. Okay, here we're looking at the number of people killed by venomous spiders and spelling bee winning words. Okay, like how many letters they are. If you look at just the graph, they look very related, right? They look extremely related. The patterns are the same. But does that mean that the number of people killed by venomous spiders causes spelling bee winning words to be more letters? No, that's ridiculous, right? They're not related whatsoever. Okay? Not at all. Correlation does not mean causation. Here's another great example. Okay, this is looking at the year. This is just hilarious to me. And I know I'm getting all nerdy again, but we're looking at the years, but we're looking at sociology doctorates awarded. So how many people get a doctorate in sociology versus worldwide non-commercial space launches. So how many people get sociology doctorates versus the space launches? If we just look at this data, it is not spread out. It is very consistent. The pattern is very similar. When it dips, when one dips, the other dips. When it goes up, the other goes up, right? It is very related. The correlation coefficient here would be pretty dang strong. But does that mean that the more people who get sociology doctorates cause more space launches? No, they're not related whatsoever. This correlation does not mean causation. I think this is my favorite one. I'm just giggling already thinking about it. Okay, this graph shows can't even get through it. This graph shows the number of films Nicolas Cage appeared in based on the year, and the number of people who drowned by falling into a swimming pool. And yes, this part's sad, but I really shouldn't be laughing. The data is, if you calculate the correlation coefficient, which has been done, it's actually moderately strong. Okay, but does that mean that the number of films Nick Cage appears in year by year causes people to fall into a swimming pool and drown? No, they are not related whatsoever. The correlation between them does not mean that one caused the other. Oh, there's so many really good ones, you guys. I just have to show you all of them because they're fantastic. And if you want, you can probably just exit out of this, but it's funny. Let's keep going. This graph, we're looking at the total revenue generated by arcades and how it's related to the number of lawyers in Wyoming. Okay, but does that mean that the more lawyers there are, are, the more money our kids get. Right? No, that doesn't make any sense whatsoever. One would not cause the other. Sorry, my husband just got home, so my dogs are barking in excitement. We're almost done. Here's another good one. It's really funny, and also sad. Murders by steam, hot vapors, and hot objects as related to the age of Miss America. These are very, very strongly correlated. But again, the age of Miss America would not cause more murders, or the murders would not cause the age of Miss America to go up or down. I'm going to get through these here real quick. The number of civil engineering doctorates awarded would not in any way whatsoever cause more consumption of mozzarella cheese. And the last one, sales of sour cream does actually correlate, if you do the math, correlates with deaths from motorbike accidents. But does that mean that the more sour cream we sell, the more motorbike accidents there are? No. So biggest takeaway from this, and again, this is like, if I could teach you one thing to take away for the rest of your life, it would be that correlation does not mean causation. And this is a huge, huge deal because, and especially in the world today with all the fake news we have, right? If you ever see an article and it looks fishy, take a look at the actual data behind it. Look at the correlation coefficient and think about what other variables could be contributing to it that people maybe don't want to talk about. Okay. All right. There's my giggly end to this lesson. If you have any questions, let me know. You don't need to turn anything in for this. But if you have questions, let me know. Hope you enjoyed those awesome correlation graphs.